Hi everybody, this is your Tobacco Auctioneer Test 2 review. So the logistics for the test are going to be pretty much like they were last time. Just remember to write legibly, to show your work if you want your partial credit, and make sure that even for questions where you think you might not need to show your work, you still do. I'm more interested in your process than your answer, so show your work if you want credit. Also remember, I'm deducting for poor units or poor notation if you don't indicate vectors, for example, correctly. That's one thing that you might get dinged on. So make sure that you show units on all your numbers and that you use good notation. You can use a 3-inch by 5-inch note card for an equation sheet, okay, but no more than that. And remember that I'm not allowing anything that has internet access in there. So you can please do bring in a calculator of some sort, but nothing with internet access is going to be allowed. Okay, we're going to cover basically chapters 4 and 5 of Matter and Interactions. We supplemented a little bit the Matter and Interactions textbook with our Kleppner and Kolenkow's Introduction to Mechanics book, and in that we drew from the polar and cylindrical coordinate stuff and the lecture on coding circular motion, that online lecture. But remember, I'm not testing you on your VPython skills on tests. There will be a derivation on the test. It's going to be one of these three. Proof that the Young's modulus can be written as K over D. The proof for the amplitude of a simple harmonic oscillator given an initial position and initial velocity, and also the phase constant of a simple harmonic oscillator given both an initial position and initial velocity. One of those three will be on the test. Okay, chapter 4. It was a long chapter, and one of the main thrusts of the chapter is that we modeled a solid material as balls and springs, where the balls were the atoms and the springs were the bonds in between the atoms. And we used that model, which is a modified Einstein-Devine model, to talk about a lot of different forces, like normal forces, tension, friction, etc. Okay? We figured out the packing density of materials. To do that, you start with the density of the material, like for example, copper is 8.93 grams per cubic centimeter. And then you use the information off the periodic table. So for example, what you're going to use is the fact that copper, as you can see here, here's the periodic table entry for it. Copper has an atomic mass of 63.55 atomic mass units per atom. And due to the magic of Avogadro's number, this is also the number of grams of the material in 1 mole, okay? Remember, a mole is 6.022 times 10 to the 23rd. So what you can do is you use the density and do basically a unit conversion to get the number of atoms per cubic meter. Now, we did that a lot, so make sure that you can recreate that because you will for sure have to do that on the test. Once you get the number of atoms per cubic meter, then you can take the inverse of that, and it gives you meters cubed per atom, which is the volume of an atom. And then remember that we set the volume of an atom equal to d cubed for the spacing. Okay? So d was the, assuming that the atoms had a spacing center to center of d, and that each one took up a little cube of d cubed, which is incorrect, but which is a nice approximation. Doesn't work too poorly. Okay. So one of the things that we did was model tension using that ball spring model. We imagined what happened in tension of a wire or something like that is you had these chains of atoms, and the atoms were connected to one another by these little springs, right? And so what happens is that as you put something under tension, it stretches the springs out. So to do that model, we had to understand how to deal with springs in series and parallel, and we went through a little derivation showing that springs in series with one another, it lowered the spring constant. So if you had a bunch of springs, big N springs in series with one another, then the effective spring constant would be the spring constant of one spring, K, divided by N. And here, of course, K is the spring constant, which is the stiffness of a spring. Now, also springs in parallel, what that does is increase the effective spring constant. And so if you have big N springs in parallel with one another, then it's big N times K for the effective spring constant, so it increases it quite a lot. And using that, we found the, using a tension, right, we used a degree of stretch, then we found an effective spring constant for atoms in a solid. Now, we developed a model for stress and strain. So remember that engineering stress, which is, or tensile stress, which is symbolized by the Greek letter sigma, is equal to, for tensile stress, the force that you're applying per unit cross-sectional area. Okay, so you can see here using this little cartoon that it's being pulled on by that force of tension in either direction. And that force is perpendicular to that blue cross-sectional area. So the stress is that force of tension divided by that area. And that's, of course, going to have units of pascals, which is a Newton per meter squared in SI units. Now, that stress causes the thing to stretch out. So it causes it to increase its length by some amount, delta L. And here, L is the initial length of the object, okay? So the strain is defined as the change in length over the initial length. And it turns out that the stress and the strain are linearly proportional to one another. And the proportionality constant is the Young's modulus, big Y. And it's a material property. It's different for different materials. For example, steel has a nice high Young's modulus, whereas something like rubber has a very low Young's modulus, okay? You can kind of think of this as Hooke's law, but for materials, if you'd like. So we can say that the engineering stress is equal to the force divided by the area, which is equal to the Young's modulus times the strain, which is, of course, the Young's modulus times the change in length over the initial length. Now, we also went through a derivation that I want you to be able to recreate that showed that the Young's modulus can also be related to the stiffness of one bond, and you should be able to prove that Y is approximately equal to K over D, where K is the effective spring constant of a single bond and D is the interatomic spacing. Okay, we talked about free body diagrams. Free body diagrams are pictorial representations of the forces on an object. They can be very simple sketches. You can represent things by dots or blocks or spheres or whatever you want, even if that's not what they really are. And then you use arrows to represent all the forces acting on the object. Okay? So for example, if you have a block sitting on a table, sitting still, the two forces at play would be the normal force, indicated by the red arrow, and gravity, mg, indicated by the black arrow. Of course, they get a lot harder than that, okay? Now, you can solve problems with Newton's laws using free body diagrams. The first step is always to draw a little sketch like that, okay? Draw all the forces acting on the object in your sketch, okay? So, for example, here, this little boat's getting tugged on by two people, shown here. And in your free body diagram, you want to include an origin, so you can see that X and Y are labeled here in this drawing, all right? And then what you want to do is all the forces that you've labeled in your sketch there, all right, you're going to take those and resolve them into their vector components. And then you're going to sum up the forces in all the directions, the sum of the forces in X, the sum of the forces in Y, for example, here, okay? And you're going to plug the X components into the sum of the forces in X equation and the Y components into the sum of the forces in Y equation. You don't plug X into Y and vice versa, okay? And you apply Newton's second law to each component. So you sum up those forces, and then you set them equal to the mass times the acceleration in that direction. All right. Now, once you've done all that, then you solve. So don't try to skip right to steps 4 and 5. Make sure that you give steps 1, 2, and 3 their due diligence. We've done a lot of problems now using this stuff, so make sure that you do that all correctly. Okay, continuing our laundry list of forces that might occur in these free body diagrams, we've got friction. And so static friction is the friction for objects that are not sliding with respect to one another. So here you have a trash can, for example, that has a force acting on it. Somebody's pushing it, I guess, to the right. But the trash can isn't going anywhere. Okay, it's not sliding on the ground. And so there must be a force opposite to that, and it's the force of static friction that's holding it in place. Now remember that static friction is equal to a coefficient of friction times the normal force, but static friction can oppose an applied force up to a threshold applied force, and then after that the object will start to slide. And so that's why here in this magnitude equation we have the force of static friction is less than or equal to the coefficient of static friction times the normal force, right? Because static friction can oppose the applied force up to its threshold, and then after that you can exceed it, and then it'll start to slide. Okay? We also have kinetic friction. So kinetic friction acts when the object is in motion. Specifically, kinetic friction is for surfaces that are sliding with respect to one another. Okay? Now, if something is rolling without slipping, right, then that is not kinetic friction. That's actually static friction. Kinetic friction for a tire on a road would be if the tire were slipping or skidding on the road, okay? Now, the coefficients of friction vary, but we're going to neglect anything like that, any variations. We're going to assume that you have these beautiful tables of friction coefficients that are these sacrosanct things, which isn't true. But you can write the magnitude of the kinetic friction as the coefficient of kinetic friction mu sub k times the normal force. Right? A note here about normal forces. Make sure that you understand that normal forces are... Okay, so make sure that you understand about normal forces. Normal forces don't always equal the weight, mg. Okay, normal forces can be different from mg in a lot of circumstances, but here's a few of them. So they can be different from mg if there's some kind of force on the object that's acting in a vertical direction. Like, for example, if you've got a cable connected to an object that's sitting on the ground and the cable is pulling up on the object, then that will reduce the normal force. Or if there's an object that you're pushing downward on for some reason, then that can increase the normal force. If you have an object that's sitting on a sloped surface, the normal force won't equal to mg either, okay? It'll be mitigated by the slope of the surface, and the larger the angle, the lower the normal force will be. And also remember always that normal force is a contact force in between two surfaces. So for example, if I take a block and I push that block against the wall, then mg doesn't have anything to do with the normal force. It's how hard I'm pushing the block into the wall. And in that case, the normal force isn't even vertical, okay? So just be real careful and don't do that blind writing down of mg equal to the normal force when it doesn't actually equal that, okay? All right. Let's talk about sound waves. Sound waves are longitudinal waves, and that means that the oscillation is parallel to the direction of propagation. There are compressions and expansions. Expansions sometimes rarefactions of the medium through which they travel. And you can think of them as pressure waves. Remember that pressure is a force per unit area, and it has SI units of Pascal. These compressions and expansions are caused by the vibrations of the atoms in the medium, okay? Now, also remember our ideal gas law. So you're not going to have to do ideal gas law problems on the test. It just helps you to conceptually understand what's going on with sound waves. So PV is equal to NKT is the ideal gas law, where K here, K sub B is Boltzmann's constant, okay? P and V are the pressure and the volume, and N is the number of particles, and T is the temperature. So you can look here, the pressure, rearranging the ideal gas law, is N over V times KB times T. So the pressure wave in sound, in air, for example, is caused by a localized change in the air density, right? And so that's what I mean when I say that atoms in a material are getting closer together or pulling apart. It's a pressure wave, okay? Remember that we found expressions for the speed of sound in solids. The Young's modulus of the material, remember, is y. The density of the material is symbolized by rho. D is the spacing in between atoms. And so the speed of sound in a medium is equal to the square root of an elastic property over an inertial property. I think you might remember we said that in a lecture. So for a solid, the speed of sound in a solid is the square root of the Young's modulus divided by the density of the material. And then remember that we wrote the Young's modulus is K over D, and then for a single atom, the density would be the mass divided by d cubed, which is the volume that that atom occupies. And so we can then simplify this expression to be d times the square root of k over m, where root k over m is often referred to as the angular frequency of oscillation for a harmonic oscillator. So that's omega d. For the speed of sound in a liquid or a gas, it's a little different because you can't put a solid, you can't put a liquid or a gas, I guess I should say gas, sorry, gas or a liquid under tensile stress, but you can put them under pressure. And so in those cases, you use the bulk modulus instead of the Young's modulus. And so you can write the speed of sound in a liquid or gas as V is equal to the square root of the bulk modulus divided by the density. Okay, so it's still, you know, an elastic property divided by an inertial property of the material. So remember that our ball spring model doesn't work well for liquids or gases. It only works for solids, and that's because in air and in most liquids, the molecules are so far apart and so loosely bound that the spring analogy doesn't really work anymore. And in ideal gases, for example, we say that the molecules aren't attracted to one another at all, so there's no springs, okay? So there you go. I've been talking about the density. Let's review that real quick. The density of an object, its mass per unit volume. And so the SI unit for that is kilograms per cubic meter. But we often use, especially in these little problems with, finding the number of atoms per unit volume, we use density in units of grams per cubic centimeter, okay? So just remember that most materials, if you've got it in grams per cubic centimeter, it'll be on the order of 1 to 10 grams per cubic centimeter. But if it's kilograms per cubic meter, it'll be on the order of 1,000 to 10,000. So it's just a nice ballpark thing to remember in case you start to confuse yourself. All right, we talked about fluids a little bit, and we did some problems with pressure and depth and all that good stuff. And we said that there's a pressure difference the deeper you go into a fluid. And so that pressure difference, delta P, will be equal to rho GH, where the rho is the fluid density, G is the acceleration due to gravity, which is 9.8 meters per second squared, and H is the height between depths, okay? And that describes pressure differences that are between two levels of the same fluid. Atmospheric pressure here. If a liquid is open to the atmosphere, and P1 is the pressure at the surface of the liquid, then P1 is the atmospheric pressure. Okay? Now, I would give you 1 atmosphere of pressure. I would give you this conversion, but sometimes it's nice to recognize numbers when you see them. And so 1 atmosphere of pressure is 1.013 times 10 to the 5th pascals. Okay? There's other weird units for pressure that you might see, but the pascal is the SI unit. Okay? Remember that pressure pushes in from all sides. Okay, so for example, if you have something that you pull a vacuum on, there's going to be a pressure pushing in on all sides from that. But this pressure doesn't crush us as human beings because we have internal pressure as well. Okay, let's talk about buoyancy and Archimedes' principle. Let's say that you have an object submerged in a fluid, as is shown here. Then there's going to be a net force on the object because the pressure at the top and the pressure at the bottom of this object are different, as we saw from this equation right here. There'll be a pressure difference because of the height difference in between the object, between the top and the bottom of it. Okay? So in other words, F1 here on the top is going to be less in magnitude than F2. So if you wanted to find the force of buoyancy, then you would take the difference of these two forces. And the difference of the two forces would be equal to rho G times delta H times A, which is the mass of the fluid that is displaced by the object times G. So in other words, the force of buoyancy that an object feels in a fluid is equal to the weight of the fluid that's displaced by the object. Okay, so that's kind of a whirlwind tour. There was a lot of stuff in Chapter 4. Make sure you review those homeworks very carefully and make sure that you can do the calculations for the Young's modulus, that you can find the effective spring constant for bonds, and that you can do manipulations like the homework problems. Okay, Chapter 5, determining forces from motion. This chapter had mostly stuff about circular motion, okay? In order to do some of the derivations that we did for circular motion, we first reviewed the dot product. Remember that the dot product or scalar product of two vectors is a way to multiply two vectors and get a scalar out. And so here it shows that the dot product between vector A and vector B, the magnitude of that dot product will be the length of A times the length of B times the cosine of the angle in between A and B. And another way to write that is to say, where is it, that the x components of A and B multiplied times one another plus the y components of A and B multiplied times one another plus the z components of A and B multiplied times one another. That'll also give you the dot product. But I skipped ahead just a little bit. The dot product is commutative, so if you take the dot product of two vectors, A dot B, that's going to be equal to B dot A, and it also obeys the distributive law. A dot B plus C is equal to A dot B plus A dot C. Remember that in vector notation, we often use unit vectors to indicate the components, okay? And so the I hat is the x component, the j hat is the y component, and the k hat is the z component. Remember that when you're doing the dot products of unit vectors, the dot product of a unit vector with itself is 1, and the dot product of any unit vector with a perpendicular unit vector is going to be 0. And that's because of that cosine theta term, right? The x and y directions are perpendicular to one another, so I hat dot j hat would be, 1 times the cosine of 90 degrees, which is 0. So if you're going to use that component form with vectors, this is how you would write them out. The other notation that's acceptable, of course, is that triangular bracket notation to indicate the x, y, and z components. Okay, we also reviewed polar coordinates. Polar coordinates and Cartesian coordinates can be related to one another through trigonometric identities. But first, polar coordinates are usually given in 2D as r and theta, where r is the distance of the point from the origin, and theta is the angle that connects the position vector for the object with its coordinates x, y. It connects the origin to that. It's the line that connects it, the vector that connects it. And then theta is the angle that swings counterclockwise from the plus x-axis to the position vector. If you're trying to find the polar or Cartesian coordinates from one another, you can use your trig like I said. R is going to be the length or the hypotenuse of that vector. X and Y are the x and y components. And that means that your angle theta that swings from the plus x-axis can give you, using cosine and sine and tangent, can give you the components. So just make sure that you remember your trig. If you're going to use x is equal to r cosine theta and y is equal to r sine theta, that'll work fine as long as theta is always defined as the angle that swings counterclockwise from the plus x-axis. If your angle theta is from a different axis, for example, or it swings the other way, then these formulae won't work. Okay, we talked about circular motion. Remember that for an object to be in uniform circular motion, there has to be a net force that acts on it, okay? And that's because if an object is moving in a circle, it's constantly changing direction, right? And since the change of direction is the change in the position vector of the object, then that means there's got to be a force acting on it to get something to change its direction. Okay, so the centripetal force is the inward force that's supplied by something else, right? So if something's in circular motion, for example, there is a centripetal force. But for example, for this hand whirling the ball on the string, it's the tension force that's causing that centripetal force. So centripetal force isn't a force in and of itself. It's always supplied by something else. And as such, it's always the result, the right-hand side of your sum of the forces equations, okay? So the centripetal force is given by mv squared over r, where m is the mass, v is the speed, and r is the radius of the circle. And remember that you can relate the speed of the object to its radius and its period via the equation v is equal to 2 pi r over t. And this is just the distance divided by the time. So here t is the amount of time that it takes to go around the circle one time, and the distance traveled in that time is the circumference of the circle, which is 2 pi r. So the v is 2 pi r over t. Remember that you can relate the period to the frequency of the rotation. The period t is equal to 1 over f, where f is the frequency. So that relationship is always there for you. Okay, we talked about angular displacements, angular velocities, and angular accelerations. So let's review those definitions. An angular displacement is an angular change for a rotating object. So for example, this wheel here has rotated through an angle and in some amount of time, and the angular displacement for that wheel could be written as theta 2 minus theta 1. Remember that if you have a counterclockwise rotation, that's defined to be a positive angular displacement, and if you have a clockwise rotation, that's going to be defined to be a negative displacement, angular displacement, and that's just the convention that we use. Remember that in order for these equations for the angular quantities to work, it's best to have them in the SI unit of angular displacement, which is the radian. And remember that there's 2 pi radians in 360 degrees, and so you can use that always to do your conversion if you need to from degrees to radians. Okay, the angular speed, the average angular speed, is the angular displacement divided by the change in time. So omega average is delta theta over delta t. And then if you take the limit of that as delta t goes to 0, then you have omega is equal to d theta dt, and that's your instantaneous angular velocity. I don't know why my d omega dt went away, but there you go. I'll fix it. Hang on. There you go. Now it's fixed. So omega, the instantaneous angular velocity, is equal to d omega dt, or d theta dt. Dang it, I didn't fix it. Hang on. I'm going to fix it right now. There we go. D theta dt. Okay. Now, the average angular acceleration is the rate at which the angular velocity changes with time. So alpha average is equal to delta omega over delta t, and then the instantaneous acceleration is the limit of that as delta t goes to 0, which is d omega dt. Okay? So you can change your angular speed as well. Remember how to relate angular quantities and linear quantities. So if something goes through an angular displacement and it's located at some distance r from the center of rotation, we can say that the translational displacement that makes, the arc of the circle that's subtended s, is going to equal to r times theta. And then we can relate any rotational quantity to its analog linear quantity by multiplying by r. So for example, speeds or velocities, v is equal to omega r, and the acceleration, the tangential acceleration, is equal to alpha times r. Okay? So remember that every point on a rotating object has the same angular motion, but every point on a rotating object does not have the same linear motion, because if you're further from the rotation axis, r is larger, and that means that your linear quantity is going to be different. Remember that if you have an object that is rolling, not just rotating, but using that rotation to roll, especially when it's called rolling without slipping, right? And that means that you're not skidding on the surface, that the point on the wheel, for example, isn't sliding over the surface, but rather each individual point on the wheel remains stationary with respect to the ground while it's in contact with it, okay? If you do that, then s is equal to r theta, and so the distance that the wheel rolls, s, is going to equal to r theta. So, for example, you can relate the tangential motion to the actual distance traveled, okay? So s is r theta, and the velocity of the center of mass would be r times omega. So the center of mass of the wheel would be moving at r times omega, and the acceleration of the center of mass would also be r alpha, okay? We talked about that in class. Okay, now speaking of angular accelerations, all right, remember always that circular motion doesn't have to be beautiful, perfect, and uniform all the time, okay? Something can have an angular acceleration. And remember that what causes a change in a particle's direction or speed is going to be always a force. So let's say that you have an object moving through some kind of circular motion, and you're going to write out the total force acting on that object. And we're going to say that at any given time, you could have some random force pointing in some random direction acting on that object. But we're going to break that force into parallel and perpendicular components. And so the parallel components are going to be considered to be the components of the force that are in the direction of the current velocity or momentum of the particle. And the perpendicular components are going to be the components of that force that are perpendicular to the velocity or the momentum of that particle. So we can say that F is equal to F parallel plus F perp, right? Now, remember that Newton's second law says that the force is equal to dp dt, where p is the momentum of the particle, so the force is the time rate of change of the momentum. And so that must mean that you have a dp dt that's parallel and a dp dt that's perpendicular to the current momentum of the particle. So where does this come from? Well, remember that you can always write a vector as its magnitude times its unit vector. So p, for example, is the magnitude of p times p hat, right? And p hat is the unit vector that points in the direction of the momentum. So magnitude times the unit vector. Now, if you take the time derivative of p with respect to time, d dt of p hat, then applying this product rule, chain rule, anyway, I always forget. Then first you take the derivative of the p part, so that would be dp dt times p hat, and then you would take the derivative of the p hat part, so that would be plus p dp hat dt, okay? So basically, you can look at it and see that if the magnitude of dp dt is changing, then that would mean that the speed is changing, and that's going to be our f parallel part. And if dp hat dt is changing, then that's going to cause a change of direction of the particle because the unit vector is changing. And so that's going to be the f perpendicular part. So to sum up, different changes in a particle's motion can produce an acceleration or a force. These things can cause the magnitude of the velocity vector or the speed to change, and that's caused by a parallel component of the force. And then if the direction of the velocity vector changes, right, even if the magnitude remains constant, then that means that there's a perpendicular component of the force. So, in other words, if an object's in centripetal or in circular motion, the centripetal force will be this f perp because it's causing the velocity vector direction to change. But if there's a tangential force, then that causes the speed of the object to change, which means that you have an angular acceleration. All right? And you can also have both. So you can have a force that has both parallel and perpendicular components and change the speed and the direction. And that's possible too. So that's kind of depicted here, where we have this acceleration vector that's pointing in this random direction, and it's got the radial and the tangential components that's causing both the speed and the direction of it to change. Okay? If that's the case, then you can do a sum of those two things, but remember it's a vector sum. And so to find the magnitude of the total acceleration, it would have to be the square root of the sum of the squares of the tangential and the centripetal accelerations. Remember that the tangential acceleration is r alpha, and then you can write the centripetal acceleration as r omega squared. And so that would mean that your total acceleration vector could be written as r times the square root of alpha squared plus omega to the fourth. Now, we went through all of this stuff very carefully in lecture. So if any of the things that I just said in this very brief tobacco auctioneer review sound completely unfamiliar, then what that means is that you need to go back and you need to review the notes for that lecture within chapters 4 and 5 and really do a deep dive here. You're not to treat this very quick review as a substitute for having heard and understood the information well the first time. I hope that is clear. And if you have any questions, let me know, and I'll see you in class.